Welcome. Let us discuss today about FIR filter design using Fourier Series method. Right now, in this method, first step, let us discuss the design procedure or procedure steps. Design procedure. So, step one, first step, what we discuss is, so let us identify so desired transfer function and identify cutoff frequency and also identify the number of samples or number of stages. Okay, so desired transfer function, we write it as transfer function is denoted by capital X. So desired I denoting by D. So this transfer function is continuous in frequency domain, so omega. So cutoff frequency we know it is omega c, and number of samples we know it is total number of samples are n. So this is the first step. Let us identify from the given information. So I want to design a FIR filter. So what is our required or what is our desired transfer function we have to find? Capital HD of e power omega. This is given. We identify this. Cutoff frequency may be given and total number of samples also will be given. So next step is step 2. Next step is, so from frequency domain I want to convert to time domain. So from frequency to time domain we have a relation. This time whatever you want is, since it is a digital system we are talking, time is discrete time I want. So discrete time, the capital H, when I want in discrete time it is small h. So it is also desired. In time domain, discrete time domain is n. So this is nothing but, so to find desired impulse response. So this is our next thing. How do I get desired impulse response? So relation between impulse response and transfer function. So this is in time domain, discrete time. This is in frequency domain. So from frequency, if I want time domain, I will take inverse discrete time Fourier transform of the given transfer function capital HD of e power j omega. Right? So what is the formula we try to take for inverse discrete time Fourier transform? It is 1 upon 2 pi integral. Why I am taking 2 pi, why I am dividing by 2 pi is because we are considering the given signal in the limits minus pi to plus pi. Okay, so from minus pi to pi overall range is 2 pi, so 1 by 2 pi times minus pi to pi. So here I am integrating the given transfer function capital HD of e power j omega multiplied by e power j omega n. Since it is inverse, I am taking positive j. Okay, e power j omega. So this function is in omega, so I will integrate with respect to omega. So this is the formula to find impulse response, desired impulse response. Now, in the second step, we need to concentrate, we need to identify 2 points. So point 1, what is the 2 points? Point 1 is this, what is the first point is, okay, now point 1 to be noted. Now we understand that this impulse response, which is in time domain n range is from minus infinite to plus infinite. This is the range of n. That is the first point. So the limits of n are infinite range. So whatever the impulse response I have, it is of infinite range. So impulse response which has infinite range. So infinite impulse response. So what is the second point to be noted? We understand what here this impulse, with this impulse response we can take, or we discuss the second point in the next step. So now here we got infinite impulse response, but what we want is finite impulse response. So how can I get finite impulse response? So that is our step 3. So step 3, so whatever the infinite range we have, suppose if I take this is number line, it is from minus infinite to plus infinite. This is infinite range. Now I want a finite range. When I want a finite range, so what we try to do, we are trying to take the signal it is symmetrical on either sides at origin. So when I want finite range, this is the finite range. So finite range, this should have overall, it should have n samples. So when I am taking n samples, half right side, half left side, including 0. If I exclude 0 from n, if I exclude 0, I will get n minus 1. So overall n minus 1, half this side, half this side. So this will be, now this will be n minus 1 by 2. So this range should be also n minus 1 by 2 to negative side. So the range of this, now I want finite range, since here it is n samples I am considering, it is minus half n minus 1 to plus n minus 1 by 2. So now if I am taking the finite limits from the overall infinite limits, that we are calling it as truncation. So we are calling it as truncation. So third step is what? Truncating the desired impulse response. When I truncate impulse response, whatever I get, again I get impulse response only h of n. So h of n is impulse response which is finite. So this is finite impulse response I am getting. So this finite impulse response obtained from this infinite range impulse response, which is considered from where n is, range of n is from, so minus of n minus 1 by 2 to plus n minus 1 by 2. So this is the range of n. So here, now what is that we understood now? What is the point? Here I said, what is the point we need to understand? We need to understand this impulse response is symmetrical about, now it is either side. So since it is symmetrical, so h of n becomes h of minus n. So this is the important point to be noted in third step. Then next step is, once we get the impulse response, now I want to find transfer function by applying Z transform. So apply Z transform, will get the transfer function or impulse response, frequency response, whatever I get. So that is, this is a function capital H of Z. So that is nothing but, so Z transform of this H of n. When you take Z transform of H of n, we know the formula is summation. Now range is, limits is nothing but what? Minus of n minus 1 by 2 to plus n minus 1 by 2. So now this H of n is multiplied by Z power minus n. Now let us see what we have done till this step. The first step is, we have given transfer function, desired transfer function capital H d of e power omega we identified, and cutoff frequency and total number of samples capital N we identified. Next, from this transfer function we want impulse response. So desired impulse response is capital H d of n, nothing but inverse discrete time Fourier transform of this given transfer function. So inverse DTFT formula is 1 by 2 pi times minus pi to pi. So this is given transfer function in t power j omega n. This is in frequency, so integrating with respect to omega. So now once we get this impulse response which is desired, now this range is, the value of n range is from minus infinite to infinite. So it is infinite range, we are calling it as infinite impulse response. It is from minus infinite to plus infinite. But I want to design a finite impulse response. So when I want to take a finite limit, so with the n samples I am considering, so since it is either side distributed symmetrically, so if I take 0 from this n samples, I am left with n minus 1 samples. So n minus 1 overall samples, half is to the right side and half of n minus 1 samples to right side and half of n minus samples to left side is negative. So this is the range. So I want to truncate this infinite impulse response to finite impulse response. So I am truncating. So truncating the impulse response, in what limit this is? In limits minus of n minus 1 by 2 to, so plus n minus 1 by 2 to. So in these limits I am truncating the given infinite impulse response h d of n. So h of n is nothing but finite impulse response obtained from the infinite impulse response capital H d of n only. where I am taking n values between these limits minus half n minus 1 by 2 plus n minus 1. Once I get this h of n, I am applying z transform. So z is nothing but e power j omega. So I am getting frequency response, I can say, or transfer function. So I can call it as a frequency response. So now frequency response I can find capital H of z is nothing but the transform of is given impulse response capital H of n, small h of n. So z transform formula we know, summation. So instead limits, since the limits is minus n minus 1 by 2 to n minus 1 by 2, this h of n into z power minus n. So this is what we have discussed. Now we have seen h of z is nothing but frequency response is z transform of h of n. The transform is summation minus n minus 1 by 2 to n minus 1 by 2 h of n z power n. Now this minus n minus 1 by 2 to plus n minus 1 by 2, let me split this. That is from minus n minus 1 by 2 to minus 1 and at 0 and 1 to n minus 1 by 2. So when I substitute 0, h of 0, z power 0 is 1, so it's simply h of 0. So what I am trying to do, let me put, if I put n is equal to, so minus n here, so what I will get summation. Now n is negative, I am taking n becomes now minus n means both this becomes positive. So n minus 1 by 2. So here minus 1 also, since it is n is equal to minus 1, it, minus n I substitute is equal to minus 1 means n is equal to 1. So this is h of minus n. Z power, when n is minus n becomes n, right? So plus h of 0 plus summation. So n is from 1 to capital N minus 1 by 2. H of n into z power minus n. Now, if you see here, we know here already in the earlier step we have seen it is symmetrical about origin. So h of minus n is equal to h of n. So when h of minus n, if I am replacing by h of n, now this term, first term and this third term are same. So h of n into z power n, h of n into, sorry, not same, only h of n is same. So limits are same, that is 1 to n minus 1 by 2 to 1 to n minus 1 by 2. This is z power n and z power minus n. So what I can write now, if I take this second term h of 0 outside, now this is summation. Now n is from 1 to n minus 1 by 2. So this is h of n if I take common. So what I am getting here, this is z power n. So what I am getting here, this is h of n is common, these limits are same. So here it is z power minus n. So this is nothing but capital H of z. Once I get this capital H of z, now we observe that this impulse response earlier h of n, now we am taking from limits minus n minus 1 by 2 to plus n minus 1 by 2. This impulse response is now in the range of n minus 1 by 2 to plus n minus 1 by 2. So this is having negative and positive limits. So this is non-causal system. So non-causals are non-practical systems. So non-practical systems. So to make it causal, so this minus negative limits whatever is there, I am shifting to right side. If I shift to n minus 1 by 2 2 times to right side, so that becomes now shift by n minus 1 by 2 units right side. So in time domain I am shifting by n minus 1 by 2 units to the right side. Okay. So why I am shifting this here? We are shifting to make it. If I shift now, this is becoming causal system. So this is a causal system. So when I am shifting in time domain, okay. Now what happens now? H of n. So when I shifted now, it became now here h of n. When I shifted, it became h of n minus. So right side it is subtraction, n minus what units it has shifted, n minus 1 by 2. So when I shifted in time domain, I am finding in frequency z domain is if I apply z transform, I am getting capital H of z. So here when I shifted, what is happened? This capital H of z is multiplied by z power this minus of n minus 1 by 2. So this we need to understand now. So next step is what now? So step 5. So step 5 is multiplying by z power n minus multiplying by z power minus of n minus 1 by 2. So multiply by z power minus of n minus 1 by 2. So for this h of z, when I multiply by z power minus of n minus 1 by 2, let me assume this is h dash of z. And simply I am multiplying. So h of z already we have, that is z power minus of n minus 1 by 2 outside bracket. This h of z value we have, that is h of 0 plus summation. Now n is from 1 to n minus 1 by 2. This is h of n outside z power n plus z power minus n. So now we will multiply this to each term. So we get we are getting this frequency response. So once we get the frequency response, now last step is nothing but we try to find the magnitude of this. So we'll try to plot. Let me write here a simple step. So step 6 is plot magnitude frequency response magnitude of. So magnitude is nothing modulus of h dash of z. Okay. So we want to plot with respect to frequency. How do you get this magnitude? The simple formula is h of 0 plus summation 2 times of h of n into cos omega n. So these limits of n are from 1 to n minus 1 by 2. So this is what simple point we need to understand. When I want to get the magnitude frequency response, so I can simply take h of 0 plus summation. One is summation limits are from 1 to n minus 1 by 2. So 2 times of this 2 times of h of n into cos omega n, right? So this is the sixth step what we are trying to get. Once I get this magnitude, I will plot this. This magnitude of this h dash of z versus frequency omega. Z is nothing but e power j omega. I can write h dash of e power j omega versus omega. This I am trying to plot. This is our final step. Okay. So let me just as a quickly we understand these are 6 steps what we have seen. Okay. Let us see graphically what we have seen the steps now. First step is given transfer function. So this is desired transfer function. From that we applied IDFT, inverse discrete type Fourier transform. To this I got this is infinite impulse response. So this is the transfer function given. Once I get this infinite impulse response is in the infinite range. So now once I get this, now I am finding out, I am truncating this. So we are truncating in the limits minus n minus 1 by 2 plus n minus 1 by 2. So same impulse response I am considering in a finite range. So this is a finite impulse response. Once I get finite impulse response, I am applying Z transform. And once I apply Z transform, I get this frequency response. Okay, once I get frequency response, now here this is a non-causal, this is a non-causal. So we make it causal by shifting to right side n minus 1 by 2. Shifting n minus 1 by 2 in time domain is nothing but multiplied by z power n minus 1 by 2. So this is nothing but shifted, sorry, right shift by n minus 1 by 2 units is nothing but right shift by n minus 1 by 2 units, nothing but multiplied by z power minus of n minus 1 by 2. Whatever is multiplying to this transfer function or frequency response z power minus n by 2, if I assume as z dash of z, last step is nothing but we are trying to plot. So this graphically if you see, if we assume as we discussed now this transfer function, so is considered in the periodic limits of minus pi to plus pi. Minus pi to plus pi I am taking, this is omega, this is capital H of e power j omega. Now as we discussed, now if I am, for example, I am considering a common example. So let me take a gate function. So gate function, if I take a low pass filter, so if it is a low pass filter, let me consider this low pass filter in the cutoff frequency is minus omega c to plus omega c. So cutoff frequency of this low pass filter is omega c. So now what we understand from this example we are considering, if I take a transfer function, so minus pi to omega c, from minus omega to omega c amplitude is 1, from omega c to pi it is 0, right? Now second step, here this transfer function may apply inverse discrete Fourier transform, discrete time Fourier transform. We know this gate function and sinc function. Sinc function, this is a gate function. It is a gate function. So we know gate function forms Fourier transform. This forms Fourier transform pair with the sinc function, or I can say it is sampling function. Sampling function. So sinc function, if I try to draw the sinc function, now how do we get the sinc function? So this is capital HD, small hd of n. If it is amplitude, let me take a sinc function. Right? The amplitudes are decreasing. Like this. So this go on till minus infinite. So here also like this go on, this n value, this goes till infinite. This here it goes till minus infinite. So this range of n, hd of n range is nothing but minus infinite to plus infinite as we discussed. Now I am truncating between some limits, minus of n minus, this is minus of n minus 1 by 2, this is n minus 1 by 2. If I truncate only between these limits, so if I take this is minus of n minus 1 by 2, this is plus n minus 1 by 2, this range, I will get the same signal, I will get the same sinc function. So here also same sinc function. This is the limits are from minus of n minus 1 by 2. This is the limit. So this limit is plus n minus 1 by 2. This is the limits of n. So this I am writing this as what? Small h of n, impulse, finite impulse response. So from this I am shifting this to right side now in time domain. When I shift to right side by n minus 1 units, so what I will get? This signal, this 0, whatever it is, I get n minus 1 by 2. So this is at n minus 1 by 2. So let me shift this. So here also, when I shift now n minus 1 by 2, another n minus 1 by 2 times. Now these limits are n minus 1 only. Now here minus n minus 1 by 2 to plus n minus 1 by 2. When I shift, this becomes 0 now. So this is nothing but, so this is the signal which is shifted to right side, that is so small h of n minus. So shifting is nothing but capital N minus 1 by 2 units. So I am shifting this signal. So when I shifted this h of n, when I find the z transform, I am getting this h of z. So when this shifting this, for this z transform I get h of n, h of z when I find. And for this, when I find z transform, so it is shifted, it is nothing but 1 by z power n minus 1 by 2. And finally, when I try to plot this graph, now finally, now graph is nothing but magnitude of h dash of z, or magnitude of h dash of e power j omega or omega versus omega if I try magnitude. This magnitude, this is a low pass filter. I will try to get the magnitude will be, the graph is of this form. So this is the signal. Now I try to find, I try to get some, this is the signal observed in pass band. So now these are some ripples obtained in stop band. So these we are calling it as, these are called as ripples. So these ripples, undesired values. So this is we don't want these ripples to occur. The reason for occurrence of these ripples is just because of shifting, because this is a non-causal system, and this non-causal impulse response. I want to make it a causal. So to make it causal, I shifted to right side. So the signal is only on positive side. So when I am shifting to right side by n minus 1 by 2 units, due to the sudden shift of the signal, there are some ripples forming in the stop band for a low pass filter. So these ripples, whatever is forming, we are calling it as, we discuss this as the Gibbs phenomenon. Okay, Gibbs phenomenon. Now this is the drawback. So occurrence of the ripples in the stop band filter is the drawback. So in designing a FIR filter using Fourier Series method, this drawback can be achieved by a method called windowing method, that we discuss about the windowing method in our next lecture, right? So these are the disadvantages, or these are the drawbacks what we observe in our Fourier Series method. And another important last point to discuss, since we observed a low pass filter and we observed these ripples are in stop band. Suppose I take, so obviously if I take a high pass filter, if I am trying to take a high pass filter, so this is a high pass filter. Now for this, if I try to plot this graph, so it is in the reverse manner. We try to get the ripples in this pass band, and we try to get the signal. This is signal in stop band. So this graph opposite, we try to get this low pass filter corresponding frequency response. For high pass filter, this will be a corresponding frequency response, right? Now in the next lecture, we discuss the numerical. We solve problems on this designing a